This one mentions PZT, or lead zirconate titanate. Why is that material so important in ultrasound?
PZT is a piezoelectric material. It's a fancy way of saying it has a special ability. It can change mechanical energy into electrical energy, and vice versa. That's the magic behind how ultrasound transducers work. When you apply an electrical signal to a PZT crystal, it vibrates and creates those sound waves we use for imaging. And then, when those sound waves or echoes come back to the transducer, they make the PZT crystal vibrate again, which creates an electrical signal that can be turned into an image.
So PZT is like a two-way street for energy conversion. It's both the speaker and the microphone of the ultrasound world. That's fascinating. Okay, this one is about wave amplitude and intensity. I always get those two mixed up. Can you explain the difference and how they're related?
Imagine a wave in the ocean. The amplitude is the height of the wave, from the top of the crest down to the resting water level. Intensity, on the other hand, is a measure of the energy that wave is carrying. A higher amplitude wave usually has more energy, so it has higher intensity. Think about a little ripple on a lake compared to a huge crashing wave in the ocean. That crashing wave definitely has more energy.
So a higher amplitude wave would have more energy and therefore a higher intensity. Is there a specific relationship between them?
There is. Intensity is proportional to the square of the amplitude. So if you double the amplitude of the wave, you actually quadruple its intensity.
Wow, that's a pretty powerful relationship. It reminds me how a small change in one thing can have a big impact on another in physics. Now, this one mentions Snell's law, which sounds kind of intimidating. What does Snell's law all have?
Snell's law describes how sound waves bend or refract when they go from one material to another, like from one type of tissue to another. Remember that straw in the glass of water? Snell's law explains why the straw looks like it bends where it enters the water.
So it's like a mathematical formula for how sound waves navigate those boundaries between different tissues.
Exactly. Snell's law looks at the angle that the sound wave hits the boundary and the speeds of sound in those two materials to predict how much the wave will bend.
Okay, that makes sense. This one is about bit depth, which is apparently important for grayscale displays. What does that mean and why should I care about it?
Bit depth is just how many bits are used to represent each pixel in the image. In ultrasound, each pixel corresponds to a tiny piece of tissue, and the bit depth determines how many shades of gray you have to represent the echoes from that tissue. A higher bit depth means more shades of gray, which gives you a smoother, more detailed image. It's like having a bigger box of crayons. The more colors you have, the more detailed and realistic your drawing can be.
So it's like having more shades of gray to paint with, which means a more realistic image. This one asks about what happens when an ultrasound beam hits an interface at a perpendicular angle. What's so special about that?
When the ultrasound beam hits straight on, or at a 90-degree angle, there's no refraction. Remember, refraction is the bending of the sound waves as they pass from one material to another.
So it's like a special case where those sound waves don't get redirected.
Exactly. When the beam hits at a right angle, the sound waves either go straight through or they get reflected back along the same path. It depends on the difference in acoustic impedance between the two tissues.
Okay, that clears things up. This one mentions a technique called weak echo rejection. What is that, and why is it useful in ultrasound?
Weak echo rejection is a way to get rid of those really low amplitude echoes in the image. It's like turning down the background noise so you can hear the conversation better.
So it's like cleaning up the image by getting rid of the clutter.
Exactly. Weak echo rejection helps improve the contrast and make those subtle structures that might be hiding behind all those weak echoes easier to see.
That's a great tool to have in your arsenal. This one is about how hypoecho structures look in an ultrasound image. Can you remind me what hypoecho means again?
Hypoechoic structures are just structures that produce weaker echoes compared to the tissues around them. They look darker on the image because those weaker echoes are represented by darker shades of gray.
So it's all relative to the echogenicity of what's around it. What makes a structure hypoechoic?
How echogenic something is depends on its acoustic properties, things like density and how it reflects sound waves. A structure might be hypoechoic because it's less dense or because it's made of stuff that absorbs more sound energy.
I'm starting to see how all these factors come together to create the final look of that ultrasound image. This one's about color Doppler again. It asks if blue in color Doppler always represents venous flow. Is that a trick question?
It's not a trick question, but it does point out a common misconception. Remember, blue in color Doppler just means the flow is going in the opposite direction from the color red, which is usually the color for flow towards the transducer. It doesn't automatically mean it's venous flow.
So it's all about the relative direction of flow, not whether it's in a vein or artery. How do I make sure I don't make that mistake when I'm looking at color Doppler images?
The key is to pay attention to that color bar on the screen and think about the anatomy. The color bar will tell you which color is which, towards or away from the transducer. And if you know the anatomy of the area you're scanning, you can figure out if the vessels you're seeing are arteries or veins.
Okay, that makes sense. It's all about putting the pieces together. This one wants us to actually calculate the velocity of a reflector using the Doppler equation. Can you walk me through how that equation works?
The Doppler equation can look scary at first, but it's basically just a way to relate the Doppler shift, which is how much the frequency changes because of motion, to the velocity of the reflector.
Okay, but how do we actually use it to find the velocity?
The equation uses a few variables: the Doppler shift, which we can measure from the ultrasound signal, the speed of sound in tissue, which we already know, the frequency of the ultrasound wave that the machine sends out, and the angle between the ultrasound beam and the direction of flow, which we can estimate from the image.
So if we know those four things, we can plug them into the equation and get the velocity of the blood or tissue that's moving. That's amazing.
Exactly, and that's how we use Doppler ultrasound to measure things like blood flow in arteries and veins, see how heart valves are working, and even track the movement of fetal heartbeats.
This is so cool. I feel like I'm really starting to understand how we use the physics of sound waves to make these incredible images and get all this clinical information. Now this one takes us back to the basics of wave motion. It asks about the direction of particle movement in a transverse wave. Can you remind me what a transverse wave is and how it's different from a longitudinal wave?
In a transverse wave, the particles in the medium vibrate perpendicular, or at a right angle, to the direction that the wave is traveling. Like, imagine you're holding a rope and you flip your wrist up and down. The wave travels along the rope horizontally, but the particles in the rope are actually moving up and down. In a longitudinal wave, the particles vibrate in the same direction that the wave is traveling. Think of a slinky. When you push and pull on one end, the wave travels along the slinky, and the coils of the slinky are also moving back and forth in that same direction.
So ultrasound waves, which are sound waves, are longitudinal waves.
Exactly. That means the particles in the tissues are vibrating back and forth in the same direction as the ultrasound beam.
Okay, that makes sense. This one asks about intensity and how it's related to power and beam area. I'm a little fuzzy on that. Can you clarify that relationship for me?
Intensity is basically a measure of how concentrated the sound energy is. It's like comparing a spotlight to a floodlight. The spotlight has much higher intensity because that light energy is focused into a smaller area.
So if you have the same power output, a narrower beam would have higher intensity.
You got it. And that's why focusing the ultrasound beam is so important. It concentrates that sound energy into a smaller spot, which increases the intensity right at the focal point and gives you better resolution in that area.
This is starting to feel like a detective story. Each question unlocks another clue about how ultrasound works. Okay, this one asks about the relationship between frequency and wavelength. Can you refresh my memory on how those two are connected?
Frequency and wavelength are inversely proportional. That means when one goes up, the other one goes down. Think of it like a seesaw. When one side goes up, the other side has to go down.
So if the speed of sound in a particular tissue is constant, a higher frequency wave would have a shorter wavelength.
Exactly. And that relationship is important for ultrasound because it explains why those higher frequency waves give you better resolution, but they don't penetrate as deep into tissues. Lower frequency waves, they don't give you quite as much detail, but they can travel further.
It's all about picking the right frequency for the job. This one is about axial resolution testing. It asks which rod group would be used to test axial resolution. Can you explain what axial resolution testing is and how it works?
Axial resolution testing is how we check if the ultrasound system can tell apart two objects that are close together along the direction of the beam. It's like checking how good its depth perception is. We use a special phantom that has groups of rods in it, spaced at specific distances.
So if the system has good axial resolution, you'll be able to see each rod clearly, even when they're close together. But what does that have to do with rod groups?
The rod group you use for axial resolution testing is the one where the rods are lined up parallel to the direction of the beam. That way you're testing exactly how well the system can separate things along that path. If the rods start to blur together, it means the axial resolution isn't so good.
Okay, I see the logic behind that. This one is about B mode in ultrasound. What does B mode stand for and why is it so important?
B mode stands for brightness mode. It's the most common type of ultrasound imaging, and it's what creates those classic black and white images we all think of when we think of ultrasound. In B mode, the brightness of each pixel on the screen represents how strong the echo was from that spot in the body.
So stronger echoes are brighter, weaker echoes are darker, and that's how we get those shades of gray that show all the different tissues and structures.
Exactly. B mode lets us see the anatomy based on how echogenic the different tissues are. Bright areas are things that reflect sound waves really well, like bone or dense tissue. Darker areas are things that absorb more sound energy or don't reflect it as well, like fluid-filled spaces.
This is starting to make so much sense. Okay, quick one. What's the common name for lead zirconate titanate?
PZT.
Right. The wonder material that makes transducers work.